So this is the robotic arm I use for several of my projects. It has 5 servos, a base, a shoulder, an elbow, a wrist, and a gripper. Initially I wanted it to be able to pick up something in the field in front of it and then place it over on top of this black box, some sort of object. I thought that'd be pretty straightforward, just calculate a few angles for the servos to be set at and then move it. Turns out calculating these angles for this arm, given just a coordinate system, was really quite difficult. And so I'm just going to give a small video on how to calculate these angles and then apply that towards other projects. So that being said, I'll describe that here using just an X and Y coordinate system, not an X, Y, and Z. So it's only going to be 2-dimensional, not 3-dimensional. The dimensionality should not be mixed up with degrees of freedom. This is a 5 degrees of freedom robotic arm, but I'm only going to calculate 3 of the servos. So basically it's only going to be 3 degrees of freedom. So let's take a look at that. I'm going to shut this off. So here we have an x-axis and a y-axis leading up. I'm only going to deal with 2-dimension, not 3 dimensions. Not going to be a z-axis coming out at us. That gets really complicated, and I don't need to do that from this application. I did find a lot of examples on YouTube on how to calculate these angles for the robotic arm with only 2 degrees of freedom. 3 degrees of freedom nobody really talked about, and anything more than that, there wasn't any information that I could find that was readily understandable. So for my application, all I need is to calculate when the arm moves up and down like this. Now, there are limitations that need to be kept in mind. One, I'm not going through the table, so I'm doing everything from here up to 90 degrees at the y-axis. Also, I'm only dealing with the distance from here to here is 1 length, the distance from here to here is the second length, and distance from here to here is another length. So the distance from here to here is 6 inches, from here to here is 4 inches, and from here to here is 4 inches. So I have 3 lengths. 6, 4, and 4. My longest distance will be the sum of that, which is 6 plus 4 is 10, plus another 4 is 14. So anything at, say, 15 and longer, I can't reach. Anything below the table, I can't reach. And anything on the other side of this y-axis, greater than 90 degrees, I'm not going to deal with or reach either. So it's very limited. It's an arc in this area only right here. In addition to that, what I'm trying to do is I'm trying to pick up something on a table and move it to another location. That object may not be on the table, it may be up here in space somewhere. So I want to be able to reach, say, this point right here, or a point here, or wherever it may be. An example would be, let's say we have a point at 10,7. So it's 10 out on the x-axis and 7 up on the y-axis. And to do that, you need to calculate what angle to set these servos at. And there's multiple ways to do that. Initially, I'm going to have this at a starting point. For instance, maybe somewhere up here, and it'll scan the field down here, and then it'll go to that point and pick it up. But if you have something here in the middle of the field, the XY field, there's 2 ways to reach this point. You either arc down to it like this, or you can arc up to it like this. So there's a cupping up and a cupping down. In my calculations, I use the cupping down because that's actually the positive result versus the negative result. When you do these angle calculations, you'll get a plus and a minus value. And that reflects, are you approaching it from the top or are you approaching it from the bottom? And since I have to deal with a table, I opted for reaching over to the point like this. Again, I'll show you. So I'm reaching over like this, not reaching under like that. In addition, I have some other limitations. This gearbox servo here only goes from 30, or else it bottoms out, up to 65, which is vertical, not 90. So in my code, I have to account for this a little bit. Also, I do not take into account this last gripper servo because it operates a camera or some other device. So that's not part of the calculation. So I'm only doing 3 degrees of freedom. I'm doing from this leg, which is 6, this leg, which is 4, and this last leg, which is also 4. So how you can have multiple servos out here. You can have as many as you want, and they can also pivot, which I don't take into account, in and out. I'm only dealing again with a 2-dimensional plane, not 3-dimensional. Other than that, let's look at this on a piece of paper, and I'll show you that first I graphed it to get an idea how to resolve and understand what this is called. It's actually the mathematics to calculate is called inverse kinematics, or IK, and there's lots of different forms of it. And basically what it does is it takes a point in space. Let me put this back out there. It takes a point in space, and actually I'll put it back here. Point in space, and it goes backwards from this servo to this servo to this servo to that servo, calculating the angles necessary to get this arm to bend to that location. And the thing is, these are all unknowns, and the only knowns are the length of your servo arms from joint to joint, the target location, and your starting location, which is 0, 0. And given that, you form triangles to go backwards to your origin and set up and calculate out the required angles for each of the servos, or the angles of the triangle. And that's basically it. So let me show you on paper how that all works out. So I want to try to solve this and explain the formulas necessary to find the distance, to find the inverse kinematics to get from this point and this point so that all the servos line up and meet right here at this point, 10, 7. We know that this is our x-axis, this is our y-axis, so we're over 10 and up 7. We know our shoulder, elbow, and wrist lengths in inches. So let's look at the first bit of information we need. And what we need is the equation for this line that goes from 0, 0 to 10, 7. Now, this number here is the length, so that isn't pertinent for us. We need the equation, and to calculate the equation, given these knowns, we know we're at 0, 0, so x is 0, y is 0. We know our target, which is 10, 7, so x is 10, y is 7. Sometimes some websites will use h and k instead of x and y. So I have h is 10, k is 7. We'll use those equations later. We know our shoulder is 6 inches, our elbow is 4 inches, our wrist is 4 inches. The shoulder is the origin servo and the wrist is the target servo. So our first equation that we need to work on is to calculate the slope of the line. And that will be actually the slope of the line is the equation of the line. And that is given by y is equal to mx plus b. And this m is equal to k minus w divided by h minus v, and that's from these values up here. K is 7, w is 0, divided by h, which is 10, minus v, which is 0, gives us 7/10. Now we take that 7/10, because that's what m is equal to, and we plug it back into this formula. And we use y and x from up here. So we say 7, which is y, is equal to 7/10, which is m, that we calculated here, times x, which is 10, which is here, plus b, because we're trying to solve for b. We reduce that down and we get 7 is equal to 7 plus b, or b is equal to 0. So in this case, the b goes away and we get the slope, or the equation of this line, as y equals 7/10 times x. And that's important because this line is really what ties all the servos together and relates them together in order to get to this point. So now that we have the slope here, let's move on to the next equation. Let's go slowly here. To calculate a point where a line intersects a circle, fundamentally, we have two circles. We have the target radius of 4 at the target point. We have the origin radius of 6 around the origin. And we want to find the slope, you can see right here, that goes through those two circles. And this is what we have. We basically have the circle here and the circle here for the target and origin. And this is the slope of the line we just calculated. We want to know where it crosses the circle or intersects the circle. We need to find that point, because from there we can calculate this point, and that will give us our servo settings. So to do that, we use a formula in this fashion. X minus h squared plus y minus k squared is equal to the radius squared. In this case, we know the radius is 4 because we're starting from the target circle. In inverse kinematics, you have to go from the target backwards. So given that, again, we're trying to find this point. You know, is it 6 over? Is it 6.5? How far up is it? On the y-axis, we need this point, because what we're going to do is we're going to find out what this triangle is, all the sides. So we need this point in order to calculate the distance from here to here. Then we'll have this distance, and we know the radius from here to here is 6, so we'll have that distance. And once we have 3 sides of this triangle, we can calculate all these inner angles, and that'll give us our solution for here. And I'll show you how that comes together. So we take, going back to the chart here, we take x minus 10 squared plus y minus 7 equals the radius squared, which is 16. You then now need to factor this out. And I learned it using something called the FOIL method. FOIL stands for first, outer, inner, last, or FOIL. And how that works is you have x minus 10 times x minus 10. And you do the first coordinate, this and this, which gives you x squared. Then you do the inner, multiply these, and you get minus 10x. And then you do the outer, this is inner, outer first. And then you get another minus 10x. And then you do the last, which is this and that, multiplied, which gives you plus 100. You write that all out, you get x squared minus 20x plus 100. That is this equation spelled out or calculated out. Now that's only the first half of this equation you need to solve. That's this portion here. Now you have to do it for the y minus 7 portion, and it works the same way. Here we use the FOIL method. This is our equation. Now we need to take this equation and this equation and put them together and have them equal 16. So here we solve, we put them together, and actually what that would look like connected together would be x squared minus 20x plus 100, and we substitute y, which we calculated up here. And you take that y, which is 7/10 x, and you substitute that in for wherever y is that you've calculated out using the FOIL method. And that's what you get here. Y substituted becomes 7/10 x squared minus 14 times 7/10 x plus 49. There you go. So now you have this equation of y in terms of x. And that x just happens to be the slope of this line. And that's what's critical, is you're now connecting this line with this circle. And there's there's 2 points where this equation will be true. And that's what this equation is right here, is this point, and if you go straight across over here. Now this one we're not interested in because it's outside our range of servo that can reach, the reach of our servo. We want the closer one, and that's the one I always use. So that's why that's critical. So we have this equation here, and we combine both equations, and this is what it looks like when you combine the 2 equations, this equation and this equation. That equals 16. You reduce it down, you solve it, and what you get, bringing 16 over here and adding it and reducing it down, you get this equation here. And what you want to do is we're going to use what's called the quadratic equation. That's going to be the next portion of our calculation. And in order to do that, we need what's called A, B, and C. And A, B, and C are equal to this value here, that's A. This value here is B, and this value here is C. We don't need to worry about the x or the x squared. That doesn't matter. What we need is the leading number before each of those positions. And that sets up our A, B, and C, and that's what these values are here. We then take these letter values and we use the quadratic equation to solve for x. And how that equation is the opposite of b plus or minus the square root of b squared minus 4ac all divided over 2a. That's actually kind of written in C language, but this is the equation that you use. And when you solve for this, you're going to get the x value of that point. You're actually going to get the x value here and the x value over here. Now we don't want this one, so let's go ahead and solve the equation. We use the A, B, and C values from above to find the x. There will be 2 answers, one for the plus equation and one for the negative equation, because right here you have a plus and a minus. So x can either be 13.3 and it can be 6.7. I always use the smaller number. Suppose use the slope equation from above to solve for y. So if you want to find, we now have the x here, which is we're not going to use this one. We're going to use 6.7. 6.7. We substitute 6.7 back into your slope right here. And that gives us y is equal to 7/10 times 6.7, or y equals 4.7. The point where the slope crosses the circle is 6.7x, which is right about here, and 4.7, which is right about here, at this circle. And now that we know this point, we can calculate this distance. And if we know this distance, and that distance, and this distance, we can use what's called the side-side-side calculation for a triangle. And here I use the Pythagorean theorem to calculate the distance from the origin to the new point, 6.7, 4.7, and take the square root of that, and that'll give you the distance, which comes out to be 8.18. So from here to here is 8.18. Now, on the previous chart, this whole distance was 12.21. So we're only going about 2/3 of the way. Anyway, with 3 known sides, we use the side-side-side calculation to find all 3 angles of the triangle. And here's how we do it. You take the cosine of A, let's say this is A, and this is B, and this is C. And using this formula, cosine A equals B squared plus C squared minus A squared divided by 2 times BC. And cosine B is C squared plus A squared minus B squared divided by 2AC. And C squared cosine C is equal to A squared plus B squared minus C squared divided by 2 times AB. So let's look at what we have here. We know that A is going to be the length of our target circle. This is what we're trying to find the distance. We want this distance to be 4, because this is actually going to be the middle servo that has to connect this servo to this servo. And we know that that's 4, the elbow right here. If we look back here, the elbow is 4 inches. So this has to be 4. That's going to be one leg of the triangle. B, we just calculated that point. Which is 8.18, which is this distance here, right? Because we use the Pythagorean theorem from above. And then C, we know is 6, because we have a radius here, it shows it's 6. So we know that it's 4, 6, and 8.18. Now we take those letters and we plug them in for the cosine A to find this angle. And you plug them in and do the calculation, you get 0.8853 is equal to the cosine. Now you need to take the inverse, let me turn this around. You need to take the inverse cosine of 0.8853, and that gives you 27.7 degrees. So this angle right here is 27.71 degrees. Good to know. Now we do the same thing for B, and we get 108.09 degrees. And then we do the same for C. For C, and we get, in fact, what we can do is we can either use the cosine function from above here. We can either do a cosine of C, or we know that there's 180 degrees in a triangle. We can subtract A and B, and we'll get the degrees of angle C, which is 44.2. Now we have all the angles of that triangle. We need to lastly calculate the full angle of angle A. So we use the target X point as length of one side of the triangle, and the target Y point is the second length of the triangle. We then use the Pythagorean theorem to calculate the third side, the hypotenuse of the triangle. So what we're going to do is basically go from here to here to here and calculate that. And that'll give us this angle. And actually we're going to go from, we're going to go from here to here to here. And we know that this is 10. We know this is 7. And we know this is length here. And given that, we will calculate, using the Pythagorean theorem, we will calculate this angle here. So we, given 3 sides of a triangle, calculate the angle of the x-axis to the slope using the cosine A. So we can actually, since we know this length, and this length, we can substitute, we can then use the cosine C formula, and that gives us this angle equaling 27.71 degrees, which is the angle from the x-axis up to the slope line. And then from there, we want to add the 27.71 plus angle A to the angle of the slope line here. You know, so whatever this comes out to be, angle A from x-axis. And that'll be something less than 90, but that'll be your full degree up from the x-axis. And now that you have this angle and your C angle, that allows you to set this servo, but this servo is still going to be wrong. So we know what angle C is. Angle C is 44 degrees. And so the new angle C is equal to 180 minus 44.2 degrees, which is this side, which comes out to be 135.8, I think, something like that. So this angle here is 135.8, and that's what you would set that angle at. And once you do that, you will have this angle, and the large angle here, and that will get you to that point. So basically, that is how I solved it for my inverse kinematics solution. In some of the websites, they talk about using tangent or sine. This worked for me. I'm not sure it will work for everyone. I do have some websites I'll show that help you with some of the calculations of some of the functions. They get complex, so that you can make sure you're on the right path to calculating the angles and the degrees, especially with the inverse cosine. And that'll be the next step. I'll show you the code. So I want to show you some of the websites that help me calculate out these triangles and angles and that sort of thing. One of the websites is this one called mathisfun.com. It showed me here how to solve for SSS, or side triangles. Here it actually tells you that SSS is when you know 3 sides of a triangle and want to find the missing angles, and that's exactly what we wanted to do in our application. It goes in to explain the law of cosines and angles and that sort of thing. You can read this website yourself, but these are the formulas right here that I used, and came in very handy. And they have, this whole website is very straightforward. It isn't a lot of extra explanation. It's just real basic usage. And here it gives examples, and you can follow along each case. And then here it tells more information on how to subtract it from 180. And it goes on and on. So there's lots of examples in this website. I found this website to be very helpful and at least a good place to start. Another website is this one. It's called Math Papa. It allowed me to do the algebra calculator, which you can solve for x, and this was very helpful too because I could actually do very complex examples without any difficulty typing the equation in here. Some of the websites I used, it was difficult to get the equation correct, and as you're solving the angles, you want to make sure you get the equations correct so that you know that you're actually getting the right answer. And here it shows you step by step, and then it shows you the answer x equals 4. So what I liked about this was as you're programming, you want to make sure that you're getting the same value that you calculated on paper. And this helped me to go back and check the equations that I was coding in C to make sure that they're actually getting the right values. So these were two very helpful websites. I have a lot more websites I got information from, which will be in my notes here in the code. I still need to add it. I haven't added the notes, but when you download the program, the notes will be there. So here's the program, and I actually wanted to mention two things here. The first thing is earlier on in this video, I have towards the end I mentioned angle A. I misquoted and described angle. I said cosine C, which I should have said cosine A to calculate the x-axis angle A, and then you add the two values to get a total for angle A. I think I referenced cosine C, and that was a mistake. I also wanted to point out that angle A is opposite or across from line A, and angle B is opposite or across from line B, and angle C is opposite or across from line C. That's always the case. The angle is always opposite the line length that it represents. So when you do your calculations, make sure you put in the right values for A, B, and C, and that you use the right lengths for each of the lines. So that being said, let's go ahead and go through the code here. I start out with a servo because I'm moving some servos, and I have a base and a grip and a shoulder, an elbow, and a wrist. And so I'm creating the servo objects here. The counting goes from 0 to 4, so base is 0, 1, 2, 3, 4 if you want to put it in an array or something. These are some integers that I use to keep track of some values in some of the calculations. Here I set up the IK variables. I define pi in case I need to use it. The shoulder length, elbow, wrist length. Everything is float. I'm doing everything in float because you need that precision, and also when you do cosine and inverse cosine, it's a decimal, and you want to get as accurate as possible. So everything's in float, the hypothesis, the slope, point x, point y. Here I have the target endpoint. I tried some other endpoints here just to see if the calculations came out right, and they did. So in this case, it's 6, 5. I think in our example, it's 10, 7, I believe. 10, 7. I can put that back now. 10 and 7. Our origin is always 0, 0. Then we have A, B, and C. Those are the angles. And then we have positive x answer, positive y answer. And because this is part of the quadratic equation, there's negative x answer, negative y answer. Here's our angle A temp, because we have to add 2 halves to get the full angle A from the x-axis up to the actual servo arm. Angle B, and then angle C. So now we go into setup, and we do serial begin because I wanted some output. Here I set up all the pins for the base and the wrist. I might do an electromagnet, so I started to put that in. You don't really need those. Those can be removed. And then there's a switch here for the electromagnet also. So those are extras that don't necessarily need to be there. I could have removed them. I just haven't yet.
there's the base. I attach each of the pins to each of the servos. I initialize them using this function that I created down below, reset servos, that just puts it into a known position. Then that ends the setup. Here we are in the loop, and I'm basically looping from 3 to 13, and for the x value, and the y value here will go from 1 to 14. And so I'm just going to do the points. 3, x is 3, y is 1, 3, 2, 3, 3, 3, 4, 3, 5, all the way up to 314, like it showed in the video. And then I do it 4. And what it does is it just cycles all the different points that the inverse kinematics can calculate given a point in space. And this just goes through all of them. I print out the point, I print it here, and then I actually check to see if x1 is less than the shoulder length, like the shoulder length is 6. If you notice up here, shoulder length is 6. If the points that it's trying to go to are below the shoulder length of 6, let's say it's 3 or 4 or 5, and the y is also below, then I do this special calc circle. That means the circle is inside the 6-inch radius, and there's a little bit of pre-calculation you got to kind of do. It's pretty straightforward. Otherwise, the circle is outside the 6-inch radius, and you just go ahead and calculate it normally. And that's all I do for the loop. I just print out the point, and then I either call the circle inside the 6-inch radius, or I calculate the point outside the 6-inch radius. And so the calc point, and this should really probably be the special calc point. I put circle. I probably will change that. So here we have the special calc circle. And basically this is if one circle is inside the other. And so here we find the hypothesis. Take the square root of x squared plus y squared plus the wrist length. And here's the A is equal to elbow length, B is equal to the hypothesis, and C is equal to shoulder length. We then go down and calculate angle A. Angle A, again, is that calculation I showed you on paper. A cosine, which is the inverse cosine of B squared plus C squared minus A squared, all divided by 2 times BC. And then I multiply that whole thing by 180 divided by pi, and that'll give you the number of degrees. I do some special calculation here in order to get the second half of the angle A, and then I was adding it here. I have a gearbox for my robotic arm, so this is kind of unnecessary. The amount of movement that I can do, I can only go from 30 degrees up to 65 degrees. I don't even bother with this, but you may want to add it in. Angle B is equal to A cosine times the square of C plus the square of A minus the square of B, all divided by 2 times AC, divided by, again, 180 divided by pi. And I could have set this up as a variable to be degrees, but, I just didn't. I guess I could have. Lastly, here's calculate angle C, which, again, is A cosine of square of A plus the square of B minus the square of C, divided by 2 times A times B, and then convert it to degrees. And that's about it. You could very easily use this commented out line here that I commented out, where you can say angle C is equal to 180 minus angle C above. That'll give you, actually it should be, angle C would be 180 minus angle A minus angle B. So I think this is incorrect. Maybe that's why it's commented out. But you could calculate angle C just by doing the cosine, the inverse cosine, or you can subtract A and B from 180 and get angle C also. So I chose not to do that. I just did it a straight calculation. I do a little bit of fudging here because my angle A is recalculated due to the servo gearbox. I need to kind of step it down. So you might want to comment this line out. I say here, if again, I have the gearbox, if angle A is less than 35, then angle A equals 35. I don't want it to go below 35 degrees because then it hits the platform. I got a problem. After that, if it is ISNAN means is not a number. Sometimes you get a negative square root and you get back an answer that says NaN, not a number. So I am checking for is it not a number and is it not a number not, which means is it a number? So it's a negative negative. So if angle A is a number, print it out and set the shoulder servo to that angle. Give it a little bit of delay so it has time to get up there. And then I do the same thing with angle B. And I say the current angle is elbow tilt, and that's the current angle of that. And if B is greater than the current angle, then what I do is I print out the current angle, and I print out angle B. And if I set I equal to current angle, and as long as I is less than angle B, I step through writing the elbow. That way it doesn't go from, say, 90 down to 20 and just whips down there. I want it to step down nicely, and this delay gives me the option to slow it down. Like I said, I didn't really do a whole lot of speed control on this. That wasn't really my focus. And so using this, it allows me to slow down the movement of the arm. If I start to get a lot of weight on the arm, especially at the end, if I have a camera and some other devices, you start to whip that thing around, you get a lot of momentum, and it just causes havoc. So that's the top part of the if. Here's the else. Else, if it's angle B is less than current angle, I print the current angle and I print out a sign to show that it's less than, and then I step it through here also. So I goes up from the current angle up to angle B. So you got to decrement I so that it goes up, and then you just increment the elbow tilt slowly with a 5 millisecond delay. Next, I process angle C. If it is not a number, which means it is a number, then the current angle's the wrist tilt. I print out some information showing what angle I'm going to, and then I increment it slowly so that it moves smoothly. Otherwise, I decrement it, and I print it out, and then I decrement it down to the angle, and that's basically speed control. And that's the end of the special calc circle. There's this line up here. Where is it? Right here, you need to calculate that because the circle is inside the square. And in fact, I think this might need to be a minus sign if I think about it, but I don't know why. I have to double check that because we're doing the hypothesis to x1, y1. Yeah, you might want to play with that. Actually, it works with a plus, and I've forgotten why I put a plus there. But this is the special case right here. Now going on to just the normal circle calc point, where you want to find the point on the circle. You set the slope here, y2 minus y1 divided by x2 minus x1. You print the slope. Here's the slope, and I give it 4 decimal places. The target circle calc, I have a is equal to 1 plus the square root of y1 divided by x1. I had to recalculate this because when you calculate the quadratic formula, you're not solving for x. You're taking the numeric value in front of the x squared and the x and using just that. So I had to, if you have x squared, there's actually a 1 in front of that x squared. And that's where this one comes in. And then you square y1 over x1 to get the second portion. And so it may be 1 plus 0, or it may be 1 plus some other value, and that's what this value is. And that constitutes that number in front of the x squared. Same with b. If you factor it all out, you get minus 2 times x1 plus the quantity minus 2 times y1 times the slope. And that will actually give you the b quantity. It might be 5x, or it might be 10x, or it might be 7x, whatever it is. I think in our example, it was minus 20x. Well, that'll give you minus 20x. And lastly, that number, that 133 that we had in our example, can be calculated by taking the square of y plus the square of x minus the square of the wrist length. And that will give you the 133. And that's set to c. And then you take those variables and use them in the quadratic equation. And I actually made note here. If you need to set something to not a number, you take the square root, you set x equal to the square root of minus 1, and you'll get not a number. So I just kind of set that information in there in case I needed to use it. I never needed to use it, but I wanted it there. So there's two portions of the quadratic, a negative portion and a positive portion. The negative portion you calculate by getting the negative answer is equal to the opposite of b minus the square root of b squared minus 4 times ac, all divided by 2a. There you go. And the negative y answer is the slope times the negative x answer, because it's y is equal to mx plus b, which is 0. Y is equal to mx. And then you have your x and y point for the negative answer. And if it's not if it's not a number, I want to make sure it's a number. I print out that point, and then I call calc circle. And I send the negative x and the negative y point. Else, it's a positive answer. I typically use the negative answer, but in this case, if it falls through, if this becomes not a number, it'll fall through to the else. And you do exactly the same thing. Positive x answer, positive y answer. Positive x answer equals the opposite of b, plus, that's where it changes. That's a minus. That's plus the square root of b squared minus 4ac divided by 2a. And then you say positive y answer is the slope times positive x. And if it is not a number, which means it's a number, then you print it out and you call calc circle, passing positive x answer, positive y answer. And that's the end of the else. And then that's end of the calc point. And so we go down here and we pass into calculate the circle a float of the bx value and the by value. And this can be positive x or positive y, negative y. And so we're starting our circle calculations here. So the hypothesis is the square root of those two values squared. The elbow, A is equal to elbow length, B is equal to this hypothesis that we just calculated, and C is the shoulder length, because that makes up that little triangle. And then I did some calculations here. I didn't remove them because I might use them in the future, but again, this is kind of part of my servo gearbox. I can't really calculate a full angle A. It's too big of a number. So you may want to put these back in and play with it. Angle B, though, is equal to the A cosine, which is the inverse cosine of C squared plus A squared minus B squared all over 2 times AC divided by multiplied by the 180 divided by pi, which is turning it into degrees. And you get the degrees for angle B. And then same with C. You can calculate angle C here, A cosine of square of A plus the square of B minus C squared divided by 2AB times 180 divided by pi, which is converts it to degrees. Or you can just say angle C is equal to 180 minus, and I have angle C here, and I think that's supposed to be minus angle A minus angle B. So I need, actually, I just realized that's not. What I'm doing here is I'm actually calculating the full angle C, and then I am calculating the opposite side of angle C in order to get the larger angle to get to the point, because I don't want the angle inside the triangle. I want the angle outside. So I don't actually do the 180 calculation. That's what I did here. That's the same thing with this C up here. Let me go back. I know I'm jumping around a little bit, but angle C right here, there is no angle C. This is commented out because this circle is inside the 6-inch radius of the origin circle. So you don't want the angle on the the larger angle on the outside. You want the smaller angle. So you actually want to leave this commented out. That's why I did it. But a sidebar note is you could do angle C, instead of doing this calculation here, like I said, you could just do 180 minus A and B. And the same with this. Down here, I'll come back down here. Instead of calculating this, you could just do 180, angle C is equal to 180 minus AB, and then you could say angle C is equal to 180 minus angle C. And that will give you the larger angle, because here, down here, you need the larger angle. Next, we need to calculate angle A. Angle A is equal to the inverse cosine of B squared plus C squared minus A squared divided by 2BC, all times the thing that converts it to degrees. Angle A is equal to angle A times this. This nonsense is to recalculate my servo gearbox, and this is so it doesn't hit the base. If you do use angle C is equal to 180 minus angle A minus angle B, make sure you put the angle C calculation below your angle A calculation, because you won't have the correct angle A. If angle A is a number, print it out and move the shoulder to that location. If angle B is a number, set the current angle to where the elbow is, and move the elbow servo in single increments, delaying between inch increments 5 milliseconds to move slowly either down to the angle or else up to the angle. And then we have C. If C is a number, set the current angle to the wrist tilt. If it's greater, we move the servo down to the angle, else we move the servo up to, we move it, damn it, come on. We move it, else we move it up to the angle slowly in 1 degree increments with a 5 millisecond delay. And that's it. That moves all the angles. And by the time that's all done, as soon as C is done moving, we're at that point. In this case, in our example, would be 10,7. That's the end of the calculations. All that's left is to show you the reset servos. Here I reset the servo at the beginning so that I'm always starting from a known position. Eventually I might use this as like a home position to do a scan of a field, and then I can do my calculations from there. And this is just an arbitrary position. For me, my shoulder tilt at 65 is actually 90 degrees. So this is 90 degrees, 90 degrees, 90 degrees, and this is 90 degrees. So set everything basically 90 degrees. And that is the code. So I hope this kind of helps you and provides some sort of solution for your inverse kinematics calculations. I'm not 100% sure, to be honest, that this is officially the best way to do it. I know a lot of websites use tangents. Some websites discuss how to use Jacobian matrices. I didn't get into that. I had to relearn all the calculations and triangular information and sines and cosines and that sort of thing all over again. And I fiddled with a lot of paper trying to figure out how to get this all to work. This for me worked, and it was clean and it was simple. And I hope this helps. Please subscribe to my videos and leave a comment if you wish. And if you have a question, you can leave a question. Maybe somebody on the website on YouTube will answer. I don't monitor the questions and comments and stuff. I'm busy making these videos. So I hope they help, and I encourage you to share them. I'll have the code available. You can use it as you wish. I know in some cases when I was describing stuff, I might have used the wrong terminology or said things slightly wrong. I try to be consistent. However, I discuss these videos typically all in one shot, and I make mistakes, and it takes a lot of effort just to keep going. So I try not to worry about the consistency, and I try to make it up like I did here, where I told you I called the wrong angle A or C versus A. So I hope it's clear. Anyway, good luck, and I hope this helps.